Hello, class. Okay, so yeah, something came up where I won't be able to meet at our regular time. So what I want to do is go over exam 2 since we just took that. And then tomorrow we'll meet on campus and have our lab. And we should be able to get back on schedule though. We'll finish talking about one-dimensional collisions on Thursday and also briefly go into two-dimensional collisions. So that should get us back on the schedule. Okay, so yeah, I just want to go over this exam too. So let's see, problem 1. This is that one I mentioned before that I always put on the exam. A book rests on a table. The only forces on it are gravity and the normal force. Is this an example of Newton's third law? And the answer is no. We have gravity and the normal force acting on the book. So normal force and gravity. And these forces are equal in magnitude and opposite in direction. But that's not Newton's third law. So like the normal force is coming from the table, or yeah, I think the problem said the book was on the table, but whatever surface it's resting on. So the table is pushing up on the book is pushing down on the table. That's Newton's third law. Here, gravity that's coming from the earth pulling on the book is pulling back on the earth. So, the answer to that one was no. That's not an example of Newton's third law. All right, now problem 2, we have the sun and the earth, where, the sun is 2 times 10 to the 30th kilograms. The earth is about 6 times 10 to the 24th power kilograms. So the sun is much more massive than the earth. And the question says the ratio of the sun's mass to the earth's mass is 3.5 times 10 to the 5th. So that's how much more massive the sun is than the earth. And so the question is, the gravitational force that the sun exerts on the earth is, there's all the options there, then times as strong as the force that the earth exerts on the sun. And again, this is Newton's third law. The answer is 1. The force, I'll reread with the number put in. The gravitational force that the sun exerts on the earth is 1 time as strong as the force that the earth exerts on the sun. So even though the sun is much bigger than the earth, this Newton's third law. The sun pulls on the earth pulls on the sun. Those forces are equal in magnitude, opposite in direction. So even though the sun is more massive, the force is the same. Just like give that example in class, the earth pulling on this marker, the marker pulls back on the earth, the force is exactly the same. Alright, so problem 3. We have 2 masses connected by a string, and then we are exerting a 6 Newton force on one of the masses. The one to the right, they're equal masses here. So we want to know the acceleration of the system and the tension in the string that's connecting them. So we want to know the tension in that string there. So there's a couple ways we could do this, but let's break it up into 2 pieces. So like this mass on the left, the only force in the direction it's moving anyways, If it's resting on a table, there'd be gravity and a normal force. We don't care about those. They cancel each other out. So here we have tension. Now on this mass here, let's just call it M. M is 1 kilogram. For this mass, we have this applied force of 6 newtons. And we have tension pulling back. So again, more Newton's third law. Remember, we're dealing with tension like these massless and stretchless strings where they just transmit forces. So like this mass is pulling on that mass through the string. With a force T, this mass pulls back with that same force. Now if the string was able to stretch, these would, that would be, we'd have to take the string into account as well. That would be a more complicated problem. But now we can apply Newton's second law to both of these objects. Let's start with this one. So to the right, which is the direction it's going to accelerate, and that force is 6 newtons minus T. So that would equal MA. And for this one, we just have T equals MA. And if we add these equations, the minus T and T cancel out. 6N equals, remember, we have MA plus MA, but the mass is 1 kilogram, so I'll just write 2 kilograms times A. And so if we divide, we have A is equal to 3 meters per second squared. So 6 over 2 is 3. A Newton over a kilogram is a meter per second squared. Now another way you could have done that, because the string doesn't stretch, these two objects are going to move together. So we could treat this with a single mass of 2 kilograms, where that internal force would no longer be a factor. So we just have a force of 6 newtons acting on a 2 kilogram mass, would accelerate 3 meters per second squared. But then for part B, we want to find the tension in the string. Well, tension is mass times acceleration. Easiest just to look at the second equation. So we'd have 1 kilogram times 3 meters per second squared. So the tension would be 3 newtons. So like here we have 3 newtons to the right. Here we also have 3 newtons to the right, 6 minus 3. And they have the same mass, they'll accelerate together. All right. Let's move on. We've got one of everybody's favorite, a machine, simple machine. So let me draw this. So we're given the height and the mass. So the mass is 110 kilograms. See why we wouldn't want to lift that directly. Height of 2.9 meters. We're lifting it up a fair distance as well. The angle is 25 degrees. So bunch of questions here, but first off, how much force is required to raise the mass at a constant speed? So we want to lift this up. So here we have an applied force here. And gravity is of course straight down, but the component down the incline is mg sine theta. So to lift it at a constant speed, we would just have to balance that, that component of gravity down the incline. We're not dealing with friction right now. So, that's it. If we plug in the numbers, this is about 456 newtons. Okay, so that's part A. What is the ideal mechanical advantage? So let's just calculate the weight, which is mg, which is 1,078 newtons. Yeah, 110 times 9.8. And so the ideal mechanical advantage, that's what we're calculating because we're ignoring friction. That would be the force that we would have to apply without using a machine, just to lift the mass up directly. It would be 1,078 newtons divided by what we actually have to apply with the machine. So that would be about 2.37 for the ideal mechanical advantage. Now, so now in part C, we introduce this idea of a frictional force of 250 newtons. And we want to know, if we take friction into account, what is the actual mechanical advantage? So now, in this case, the applied force, I'll put a prime there because we already use applied force there. But that would be, we'd still have to balance gravity, which is 456 newtons. But we'd also have to overcome friction. So, let's see. That's 706 newtons now. So now to lift this mass at a constant speed, the applied force is 706 newtons. So the actual mechanical advantage would be the force without the machine, 1,078, over with the machine, which is 706. So that's about 1.53. So that's the actual mechanical advantage. Let's see, what else was there? How much work is required to raise the mass in the ideal case? Okay, so work, different ways we could calculate this. Let's find the length of the incline. So that's a distance. So let's see, sine of theta is h over L. So L would be h over sine of theta. If I have that number here, 6.86 meters. So that's the length of the incline we get from the triangle. And so the work done by the applied force, in both cases, for the ideal and the actual case, it'd be whatever force we apply times the length of the incline. So, we're applying a force in the direction of the displacement. So let's call that work ideal. We needed 456 newtons times 6.86 meters. So that was 3,126 joules. Now, in the actual case where we had friction, that would be 706 newtons times 6.86 meters. So 4,840 joules in the actual case. Now, if you wanted to calculate the work in the ideal case, we could just do mgh. It'd be the same as just lifting the object directly. So actually, using a machine actually takes more work. All right, so let's move on to the next problem. So we have a book on a table. Mass is 0.5 kilograms. I'm just going to draw the book, not the table. All right, so we've got a book resting on a table. So there's a downward force of 6 Newton exerted on the top of the book by hand pushing down. So you've got a book, you're pushing down on it with a force of 6 newtons. Now you also have gravity acting downwards on the book. 0.5 times 9.8 would be 4.9 newtons. So that's the hand pushing down on the book, that's gravity. So the total downward force on the book is 10.9 newtons, and so the normal force would be 10.9 newtons upwards. Okay, so problem 6. So we have a particle that's at rest at the origin of a coordinate system. So we're given the mass is 3.1 kilograms. All right. It's acted on by 2 forces. So force 1, it has an x component of 3.6 newtons and a y component of minus 2.2 newtons. So it would be like somewhat in that direction. And then we're given, these 2 forces acting on it. We're given these in component form. This is 1.8 newtons, and F2, the y component, is 3.2 newtons. So the question is, what is the position of the particle after 3.2 seconds? Okay, so we're going to use F equals ma, basic idea, to get the acceleration of the particle. We get it started at rest. And it's at the origin, so x naught is 0. And we can find the acceleration because we know the force is acting on it, and we know the mass. And just move this down a little. And once we have the acceleration, these are constant forces, then we can apply kinematics from chapter 2. So let's look at the net force in the x direction. There'll be 3.6 plus 1.8, so that'd be 5.4 newtons. And the net force in the y direction is 1.0 newtons. So from this equation, we can see that the acceleration in the x direction, that would be the net force in the x direction, divided by the mass. I'm getting 1.7 meters per second squared. And the acceleration in the y direction, we have 1 newton divided by 3.1 kilograms. That'd be about 0.32. Actually, I said chapter 2 kinematics. Really chapter 3 because, this is a 2-dimensional problem. So it's going to accelerate, straight line. It'll just, the net force is in that direction, so it'll just accelerate in that direction. But to find the coordinates at some later time, we'd have, in general, I'll just write the full equation. Just for x, not for y. In the x direction, we'd have the initial position plus the initial velocity in the x direction times time. But those first 2 terms are 0. So we would just have 1/2 ax t squared. So we'd plug in 1.7 meters per second squared. For t, we'd put in 3.2 seconds. And get the 1/2 in front. So we're getting about 8.7 meters. And y is just going to be, 1/2 AY t squared. Sorry, that's negative. The magnitude was 3.32, but yeah, we can see it's going downwards. And so the y coordinate would be minus 1.6 meters. So again, at that time, 3.2 seconds. All right, so let's move on. So problem 7. We've got 10 kilogram block that slides down an inclined plane. We're given the angle. (35 degrees). So first off, draw all forces acting on the block, including friction. So we have gravity, which is straight down. Normal force, which is always perpendicular. Normal means. And then friction, so it's sliding down the incline, so friction is opposing it. So that was it for the first problem. Now, you could break gravity into components if you want. Or you could kind of draw that separately. So like the component down the incline would be mg sine theta. That component is mg cosine theta. So now we want to know the magnitude of the normal force. Well, this is our coordinate system. Let's go with x, y like this. So in the y direction, we have simply Fn is mg cosine theta, because the net force in the y direction is 0. So these two have to cancel each other out. So let's see, I've got 80 newtons basically. I think I rounded off a little, but yeah, we've got 80 newtons for the normal force. And then if the friction force is 30 newtons, what is the acceleration of the block? So here we would have, in the x direction, going down the incline, we have mg sine of theta, and then minus the friction force, which was given, 30 newtons. That would be just mass times the acceleration. So we could plug in the numbers. You know, we know m, obviously we know g and theta. Subtract 30 newtons, and we would get an acceleration of 2.6 meters per second squared. All right, so problem 8. So a boy pulls a sled with a rope that makes an angle of 60 degrees. So let's see. The mass of the is 5 kilograms. So pulling it across a frozen pond. Pulls on it with a force of 10 newtons. And the sled moves with a constant velocity. So, what is the coefficient of friction between the sled and the ice? Okay. So, let's start I'm going to draw a free body diagram here. So acting on the sled, we have gravity. That's about 4.9 newtons for gravity. Friction, I'm just going to write mu Fn. Normal force, which is upwards, we don't know what that is. And then we have this applied force, which is an angle, so we'll break into components. So the applied force is 10 newtons. So the vertical component would be 10 newtons times the sine of that angle. Now 60 degrees is one of those special angles. This would be about 8.7 newtons. So wait, let me just check this. Yeah, I was just thinking that makes no sense because I wrote it down wrong. Yeah, force of gravity, 49 newtons, not 4.9. That would have made no sense. But, so the applied force, the component in the direction of motion, that's adjacent to the angle. So we would use cosine of 60 degrees, which is 0.5. So that would be 5 newtons. And again, it's just one of those special angles that we know. It's like 1/2 and root 3 over 2 for sine, or for the two components. So there's our free body diagram showing all the forces. So if we look in the vertical direction first, we have the normal force plus 8.7 newtons equals 49 newtons. So the normal force is about 40.3 newtons. Just by subtracting 8.7. And now in the horizontal direction, we have 5 newtons. Remember, the velocity is constant, so there's no acceleration in any direction, but in the x direction, there's no acceleration. And so the net force is 0. So we have 5 newtons equals mu k times the normal force, which is 40.3 newtons. And so if we just divide, we get a coefficient of about 0.12. Okay, so that was problem 8. Let's go back. Problem 9. So we've got let's see, let me draw this picture. That's point A, and we've got all these options here. So like A, B, C, and D. So that's a picture. Now let me read the problem. It says a ball on the end of a string is rolled with constant speed in a counterclockwise horizontal circle. At point A in the circle, the spring breaks. Which of the curves most accurately represents the path of the ball after the string breaks? And the answer is A. So again, it's just moving in this direction. So if the spring breaks, it's just going to keep on moving in that direction. All right. So problem 10. We can keep some of this. Not bad. So that's the picture for problem 10. But we have a small disc with a mass of 56 grams. It's on the end of a string. It's moving in a circle with constant speed of 2.1 meters per second. We're given a radius of 57 centimeters. So first, what is the magnitude of the acceleration of the disk? acceleration, yeah, it's moving at a constant speed. So there's no tangential acceleration, but it's moving in a circle. So there's always a centripetal acceleration equals v squared over r. And if you just plug in the numbers, you get 7.7 meters per second squared. Now, part B is what is the magnitude of the tension in the string? So if there's an acceleration inwards towards the center, there has to be a force that's coming from, we're just using F equals ma. So we'd take mass times the centripetal acceleration. And if we plug that in, we get about 0.44 newtons. Now part C was a little tricky because, if you go back and read it, and it's moving in a circle over a frictionless surface. And so question C, it says, if the string is cut, what will the speed of the disk be after 1 second? So if we cut the spring, the disk is just going to keep on moving, and it's a frictionless surface, so it'll just keep on moving with that same speed of 2.1 meters per second. All right, so let's look at problem 11. So an astronomer is studying a distant planet with a moon. So we've got a planet with a moon orbiting around it. So we measure the radius, the orbital radius, 3.84 times 10 to the 8th meters per second. And its period, it takes 2.64 months to complete an orbit. So those are things that an astronomer could conceivably just observe. Okay, so we want to know the mass of the planet. So one thing, we're given the period in months because that's a reasonable unit to measure the period of a moon. And but we want to convert that to seconds. You're given the conversion factor there. But let's apply Newton's second law. So here's the mass of the planet. Here's the moon. They've got that radius between them. And so just F equals ma. The force is Newton's law, G, capital M, lowercase m, divided by r squared. And that's equal to the acceleration is v squared over r. And so we can simplify this a little bit. Let's divide by m and multiply by r squared. So we've got that. Now, we don't know the velocity, but we know the radius and period, so we can calculate that. But generally, we can say that the velocity, so t is the time it takes to go around one circle, so the distance it travels is 2 pi r. So velocity is just distance over time, 2 pi r over t. So if we square this and plug it in, we'd have 4 pi squared r cubed over t squared. So like squaring v, we get 4 pi squared r squared over t squared. And when you multiply by r, you get an r cubed. And so the mass, that's g times m. So the mass would be 4 pi squared r cubed over gt squared. And if we plug in the numbers, getting about 6.95 times 10 to the 23rd power kilograms. So that's Kepler's law there. All right. so let's move on to problem 12. So we've got a box dragging across, dragged across the floor with a rope. So let's draw this. So let me read the problem. The numbers here. And we're given the tension in this case. And we are given the coefficient of friction. All right, now let me read the problem. So a 56 kilogram box is being dragged across the floor with a rope. Tension in the rope is 268 newtons and makes an angle of 32 degrees with respect to the horizontal. Coefficient of kinetic friction is 0.21. So first off, what is the normal force? Oh yeah, so we are dealing with friction here. So we want to know the normal force, the acceleration of the box, and if we drag the box a distance of 6 meters, what is the work done by tension? So to start out with, let's draw a free body diagram. So this here we have t cosine theta and t sine theta. So we break tension up into components. So to find the normal force, let's look in the vertical direction. We have Fn plus t sine of theta minus mg equals 0. And I think we know everything here. We know t, theta, obviously m and g. So yeah, the normal force would be mg minus t sine of theta. So I'm getting 410 newtons there. And now to find the acceleration, let's find the force of friction. So that would be 0.21 times 410 newtons. That's going to be like 82 newtons. Let me just 0.21 times 410. That's 86 newtons. And let's take t cosine theta. So cosine of 32 is about 0.84 times 268. So it's about 227 newtons here. And friction is 86 newtons. So the net force in the direction it's moving that'd be 227 minus 86. I think it's 141 newtons. And so the acceleration then, that'd be 141 newtons divided by the mass, which is 56 kilograms. So I'm getting for acceleration is 2.5 meters per second squared. Okay, now the last problem was a little bit, this is one where you have to be a little careful because now we want to know the work done by tension. And so the work done by tension, where it's moving 6 meters along the ground, this would be 227 newtons times 6 meters. So when we're calculating the work, you only want the component of the force in the direction of the displacement. And so, yeah, some people did, 268 times 6, but yeah, it's a very common mistake. But I'm getting about 1,400 newtons. Let me just check. Yeah, I rounded off a bit, but around 1,400 newtons. Yeah, and I wrote up these problems. I rounded up. This is kind of an old problem. I probably rounded off too much to get the significant figures right, but maybe better to. I should have written down more decimal places and then just rounded off at the end. But yeah, I got like 1363 roughly. But anyways, that would be to two significant figures. Oh, sorry. That should be joules. Okay. So that's problem 12. Let's look at problem 13. Now I'm going to do this one kind of quickly because, it's just a 25 kilogram bullet has a velocity of 300 meters per second. What is its kinetic energy? That's it. 1/2 mv squared. Just make sure to convert grams into kilograms and then plug in the velocity. You get about 1,100 joules in this case. So very simple, just plugging things in. Okay, now problem 14, multiple choice here. In which one of the following situations will there be an increase in kinetic energy? So it's going to lay out different situations. Which of those will result in an increase in kinetic energy? So let's do it one at a time. So a ball starts from rest and roll. Actually, I think when I wrote the answer key, I left one of the options out. Yeah, I think part A is a particle, just based on memory, I could be wrong about this, but a particle, it's moving upwards and, reaching its maximum height. And in that case, there would be a decrease in kinetic energy. It's moving upwards, it's slowing down, so less kinetic energy. The next option is a ball starts from rest and rolls downhill. So that's definitely an increase in kinetic energy. It's initially not moving, its kinetic energy is 0. As soon as it starts rolling downhill, it's got kinetic energy. So that's an increase. The next one, a box is pulled across a rough floor at a constant speed. So if the speed is constant, the kinetic energy is constant, so there'd be no increase there. A satellite travels in a circular orbit about the Earth at a fixed altitude. Now, in an elliptical orbit, there would be an increase or a decrease in energy, but like at a fixed altitude above the Earth, it's moving in circular motion, there would be no change in speed, so no change in kinetic energy. And finally, a stone at the end of a string is whirled in a horizontal circle, constant speed. Again, constant speed, no change in kinetic energy. So the only one where there was an increase in kinetic energy was the ball rolling down a hill. So it starts from rest, rolls downhill. Okay, so just 3 more. Problem 15, a car delivers 1,800 joules of energy in 3.3 seconds. So it delivers that much energy to the tires in 3.3 seconds. What is the power delivered to the wheels? Power is just energy over time. So just plugging in the numbers, about 550 watts. All right, now 16, this one is one you have to be careful with anyways. So we have this, a bead can slide on a wire without friction. So it's a circular wire with a radius of 8 centimeters. No friction. So the bead is released from the top of the loop and slides down to the ground. How fast is it moving when it hits the ground? Now, it's a circular arc, so of course you're tempted to use, this circular motion. So a lot of like that v squared over r. Problem is, this is definitely not uniform circular motion, and it starts out at rest and it's speeding up as it falls down. So the easiest way to do this problem, the key there is it slides without friction. So let's call this point A and this point B. And we can say the energy at A equals the energy at B. So it's very non-constant motion. It's speeding up. So you don't want to do kinematics here. Conservation of energy is a very easy approach to do this. And then it's kind of straightforward. At A we have potential energy, mgr, and at B, that's when it hits the ground. It has no kinetic or no potential energy, but it has kinetic energy, 1/2 mv squared. And so the mass cancels out. We get v squared would be 2gr. So just take the square root, plug in the numbers, and make sure to convert r to meters if you want your velocity in meters per second. But what I'm getting is the velocity at point B would be 1.3 meters per second. So again, remember, just the, I know a common way to approach problems is just look at what equation looks right. But again, this, the object, like you can't use kinematics here from like chapter 2 or anything, or chapter 4, because the acceleration, or the angular acceleration, if you want to look at it, in circular motion, it is not constant. The particle is just speeding up as it goes down the incline, and or down the circular arc, and it's doing so in a not constant way. The acceleration, like at any point, it would have an acceleration equal to g sine of theta, but theta would be constantly changing. It would be like that direction, like the tangential direction, which is constantly changing as you're going down the incline. And so, like nothing we've done before for kinematics, either one-dimensional, or like our xy or circular motion, will allow us to solve this problem. But conservation of energy works just fine. Okay, so one more problem. So we've got a helicopter. Let's see, a helicopter, we're given its mass. It's cruising at a speed of 56.9 meters per second at an altitude of 185 meters. What's the total mechanical energy? So here we have potential energy and kinetic energy, and we just plug everything in. I got basically 11 megajoules of energy. So mega 10 to the 6. And that's it for this exam. Now there's an extra credit thing that's posted in the Exam 2 module. So I'll put a quiz so you can upload that. but just to bring up the scores a bit. And yeah, we'll meet tomorrow on campus for lab. So that'll be it for today.